The universe did not begin with a bang, but with a question. What existed before the moment of creation is the deepest mystery in all of science. This video explores the 15 competing models of the universe before cosmic inflation, the wild theories physicists used to peer into that impossible first instant. By the end, you will understand the radically different visions for how everything came to be, from timeless quantum states to cosmic cycles of rebirth. Did our cosmos emerge from a hologram, or is it one bubble in an infinite multiverse? Each model is a complete rewrite of our origin story. Which idea of beginnings feels the most true to you? To truly grasp these 15 models, you first need to understand the profound mystery they are all trying to solve. The standard story of the Big Bang is a powerful one. It tells of a universe that was once incredibly hot and dense, expanding and cooling over billions of years to form the galaxies we see today. But this story has a missing first chapter. If you run the clock backwards, the universe gets smaller, hotter, and denser, all the way back to an initial moment of infinite density and temperature called a singularity. This is where classical physics, the rules that govern stars and planets, completely breaks down. At this point, known as the Planck epoch, our equations produce nonsense. They cannot describe what happened or what existed in that first unimaginably tiny fraction of a second. The singularity is not an answer, it is a sign that our knowledge has reached its limit. It is a cosmic curtain drawn across the very beginning. To lift that curtain, scientists proposed a bold idea: cosmic inflation. This theory suggests that a split second after the beginning, the universe underwent a breathtaking period of exponential expansion, smoothing it out and planting the seeds for all future structure. Inflation solves many puzzles, but it immediately creates a deeper one. What set inflation into motion? What was the universe like in the moment before it began? This is the primordial puzzle, the ultimate frontier. The 15 models we are about to explore are not wild guesses. They are rigorous, mathematically framed attempts to answer that single, profound question, to describe the arena of existence before our story, as we know it, even started. Our journey begins with a model that redefines the word beginning entirely. The first vision is the eternal inflation multiverse. Think not of a single starting gun, but of an ocean. A vast, restless, and eternal ocean of space-time, forever caught in a state of hyper-expansion. This is the inflaton field, a kind of cosmic energy that drives inflation. Within this churning sea, pockets of calm can spontaneously form. Through a quantum process known as false vacuum decay, a tiny region of this energetic field can suddenly drop to a lower energy state, like a bubble of steam forming in boiling water. When this happens, that bubble stops inflating internally and becomes a stable pocket universe like our own, while the furious ocean of inflation outside it continues to expand forever. In this picture, our entire cosmos is just one bubble among an infinite number, constantly being born in an endless, timeless process. There is no first bubble, no ultimate starting point, only an eternal, generative froth of cosmic creation. The implications are staggering. In each of these bubble universes, the way the bubble forms could randomly set the fundamental constants of physics. The speed of light, the strength of gravity, the mass of an electron, these might not be fine-tuned miracles but simply the local bylaws of our particular cosmic neighborhood. In another bubble, physics could be utterly different, perhaps incapable of forming stars or atoms or life as we know it. This model does not give us a singular origin story. Instead, it offers a cosmic landscape of infinite beginnings, where the very laws of nature are the result of a random quantum roll of the dice. It replaces the mystery of a first cause with the awe of an eternal, fecund process. But what if the ocean itself is not eternal, but part of a much older, rhythmic breath? The second vision is the cyclic or bouncing universe. This model asks us to let go of the idea of a single, unique beginning. Instead, it proposes a cosmos with no start and no end, only an endless, majestic pulse of expansion and contraction. In this view, the Big Bang was not the first moment, but simply the latest bounce, the most recent turning point where a collapsing universe reversed its course and began expanding once more. Each cycle lasts perhaps trillions of years, a universe living, dying, and being reborn in an infinite cosmic loop. This elegantly sidesteps the troubling singularity, as the bounce occurs when the universe is still incredibly dense, but not infinitely so. But what could possibly cause such a monumental rebound? One compelling answer comes from the epoch scenario, a story woven from the threads of string theory. Imagine our entire three-dimensional universe not as an isolated bubble, but as a vast dynamic membrane or brain floating in a higher dimensional space. Nearby, there could be another parallel brain, another entire universe, hovering just out of our dimensional reach. These brains could move through this hidden space, oscillating slowly toward and away from each other over eons. Every few trillion years, they gently collide. That collision, that meeting of worlds in a realm we cannot perceive, transfers an immense amount of energy into each brain. From our perspective inside our three-dimensional slice of reality, that event would look exactly like a hot, dense, rapidly expanding universe, a Big Bang. The model suggests our cosmos was born not from a singular point, but from a cosmic embrace in a hidden dimension. This cyclical dance offers a beautiful explanation for the universe's remarkable uniformity, as each new cycle inherits a smoothed-out structure from the previous one's long period of contraction. Our entire history of stars, galaxies, and life becomes just one chapter in an infinite, timeless book of creation and destruction, a story forever being rewritten. Yet a third vision suggests the cosmos awoke not with a roar, but with a whisper. This is the model of the emergent universe from a static seed. Picture a cosmos that was not born from a point of infinite fury, but one that simply existed, timeless and unchanging, in a state of perfect equilibrium. It was a small, closed, and stable configuration, a cosmic egg resting in an eternal quiet. This idea revives a very old concept, the Einstein static universe, a solution to his own equations that he later abandoned. In this state, the inward pull of gravity is perfectly balanced by a subtle repulsive force, a cosmological constant, creating a delicate standoff that could, in theory, last forever. But forever is a long time, and in the quantum realm, nothing is ever perfectly still. Over an unimaginable duration, tiny quantum fluctuations, the gentle hum of existence at the smallest scales, could have eventually nudged this static seed. A single, random quantum event might have tipped the balance, destabilizing that perfect equilibrium. The repulsive force could have gained a slight upper hand, and that stable seed would have begun to gently swell. What began as a minuscule perturbation would then have been amplified, perhaps triggering the runaway expansion of cosmic inflation itself. This model offers a profoundly different origin story. It replaces the violent, unknowable singularity with a serene and almost meditative past, a universe that was simply there before it decided to grow. It provides a graceful bridge between a timeless, non-expanding past and the dynamic, expanding present we inhabit. The beginning becomes not a moment of creation, but a moment of transition, a shift from one mode of being to another, sparked by the most delicate of quantum whispers. But what if the dimensions of our reality are an illusion, a magnificent projection from a simpler, more fundamental plane? The fourth vision is the holographic universe and its guiding principle, cosmological complementarity. This idea emerges not from cosmology at first, but from the strange physics of black holes. physicists discovered a profound puzzle: that all the information describing the three-dimensional matter that falls into a black hole seems to be perfectly encoded on its two-dimensional event horizon, the point of no return. It is as if the black hole's surface is a screen containing a complete description of everything within its volume. This is the principle of holographic duality, where a volume of space can be fully described by the information stored on its boundary. Now apply this breathtaking concept to the entire cosmos. In this model, the hot, dense, three-dimensional universe of the Big Bang is not the most fundamental reality. Instead, it is a projection, a hologram, encoded on a two-dimensional surface that existed at its very boundary. The Big Bang, then, is not the creation of space and time from a point, but a transformation in how information is organized. It is the moment when a two-dimensional description of reality blossomed into the three-dimensional world we perceive. This framework offers a powerful new tool to tackle the singularity, because the physics on that two-dimensional boundary may remain well-behaved even when the three-dimensional projection seems to break down into infinite densities. It suggests a radical unity where gravity in our three-dimensional world is not a separate force, but an emergent phenomenon, a consequence of the quantum information entangled on that lower dimensional surface. We are not living inside a volume, but are rather a dynamic image, a cosmic story being told on a distant, fundamental screen. Yet even a holographic projection needs a source code, a more fundamental set of rules. For that, we turn to the very fabric of reality itself. The fifth vision is string gas cosmology. This model reaches down to the most basic ingredients proposed by theoretical physics, the tiny, vibrating loops of energy called strings. In this picture, the universe did not begin as a point of infinite density, but as a hot, dense, and highly compact tangle of these fundamental strings, a seething cosmic gas. The behavior of this string gas is governed by a unique and beautiful symmetry. Strings can exist in two distinct states. They can stretch across the compact dimensions of space, winding around them like rubber bands on a tube, or they can vibrate freely, moving like particles within those dimensions. For a long time, perhaps, these winding and vibrational states were in perfect balance, locking the universe into a small, static size, reminiscent of that eternal seed. But as this hot gas of strings interacted, a remarkable transition could have occurred. Through their collisions and vibrations, the winding strings could have gradually annihilated each other, releasing energy and breaking the symmetry that held the dimensions tight. Only three of the spatial dimensions, the ones we experience, were able to unfurl and expand rapidly. The remaining extra dimensions predicted by string theory remained tightly wound and compactified, stabilized by the remaining string gas. This process did more than just explain why we live in three large dimensions. The annihilation of winding strings and the release of their energy could have directly heated the universe, creating the hot, dense plasma of the traditional Big Bang. Furthermore, the quantum fluctuations in this primordial string gas, the tiny differences in density from place to place, could have served as the perfect seeds for all future structure. In this model, the first galaxies were imprinted by the faintest whispers of vibrating strings, directly linking the smallest scales of particle physics to the largest scales of the cosmos. It offers a complete mechanical narrative where the universe emerges not from a singularity, but from the dynamic thermodynamics of its most basic constituents, a cosmos born from the music of strings. But even a cosmos born from strings must ask, what was the first note? The sixth vision offers perhaps the most elegant and mind-bending answer of all, the no-boundary proposal, often called the Hartle-Hawking state. This model confronts the singularity not by finding a cause before it, but by removing the concept of a boundary entirely. Think of our universe in its earliest moments. In classical physics, if you trace time backwards, you hit a wall, a hard edge where everything begins. The Hartle-Hawking proposal, using the tools of quantum gravity, suggests this is an illusion. There is no wall, no sharp edge to time. Instead, the beginning is smooth and rounded off like the surface of a sphere. To visualize this, consider the South Pole on Earth. You can stand at the South Pole, but the question, what lies south of the South Pole, has no meaning. There is no direction called south once you are at the pole itself. The point is not a boundary or an edge. It is simply a location where the normal rules of north and south merge. In the same way, the Hartle-Hawking proposal describes the origin of our universe not as a point of infinite density, but as a smooth, closed geometry where the dimension of time behaves like a dimension of space. In this quantum realm, there is no distinction between past and future, only a four-dimensional shape without a sharp edge. This means there was no time before the Big Bang, because time as we know it only emerges from this timeless, fuzzy quantum state. The Big Bang itself is transformed from a violent explosion into a gentle, continuous transition, a quantum blur where the universe simply becomes. It redefines the very idea of a beginning, suggesting the cosmos did not appear in time, but that time appeared with the cosmos. The profound implication is that the universe would have no need for an external creator or a first cause, because in this smooth, self-contained geometry, the question of what came before loses its footing, dissolving into the elegant, boundless geometry of reality itself. Yet even a smooth, boundless beginning must contend with the fabric of space. The seventh vision, loop quantum cosmology, asks us to reconsider what that fabric is made of. According to this model, born from the principles of loop quantum gravity, space is not a smooth, continuous sheet. It is woven from tiny, discrete loops, a fundamental fabric of reality stitched together from indivisible threads at the Planck scale. This quantum weave has a profound consequence. It cannot be squeezed into an infinitely small point. As you rewind the cosmic clock, the universe contracts, becoming denser and hotter. In classical physics, this leads inexorably to the singularity, a point of infinite density where the equations fail. But in loop quantum cosmology, as the density approaches a critical, immense value, the quantum nature of space itself pushes back. The interwoven loops of geometry create a powerful repulsive force, a kind of quantum pressure that becomes stronger than the crushing force of gravity. Instead of collapsing into nothingness, the universe reaches a minimum possible size and then rebounds, expanding outward once more. This is the Big Bounce, a cosmic rebound driven not by a collision of brains, but by the intrinsic granularity of space-time. The Big Bang is transformed from a singular beginning into the latest turning point in a potentially endless cycle of contraction and expansion. This model provides something incredibly valuable, a rigorous, mathematically sound description of the universe at its most dense moment, a bridge across the singularity that avoids the infinite breakdown. It paints a picture of a pre-inflationary phase where the universe, compressed to a seething quantum foam, was governed by these discrete geometric rules. The transition into our familiar, smooth expansion becomes a natural consequence of the universe relaxing from that ultra-dense quantum geometric state. In this vision, the cosmos breathes, its rhythm dictated not by external forces, but by the very woven threads of its own being. There is a profound elegance to the idea that the end of everything is also a beginning. The eighth vision, conformal cyclic cosmology, proposed by the renowned physicist Roger Penrose, offers a cycle of cosmic rebirth so vast it redefines the meaning of time itself. This model describes a universe not of one lifetime, but of endless eons, each lasting perhaps trillions upon trillions of years. In this breathtaking picture, the remote, cold future of our current universe does not fade into eternal darkness. Instead, it transforms seamlessly into the hot, dense Big Bang of the next. How is such an impossible transition possible? The key lies in a subtle but powerful property of physics called conformal invariance. Imagine taking a detailed map of the world and stretching it uniformly in all directions. The shapes of the continents remain perfectly preserved, even as their absolute size changes. Conformal transformations work in a similar way with spacetime, stretching or compressing all distances and durations by the same factor while preserving the angles between things, the fundamental shapes of reality. In the unimaginably distant future, when the universe has expanded to near emptiness and all matter has decayed or been consumed by black holes, something remarkable happens. With no particles left to define a fixed scale of mass or length, the universe becomes effectively scale-less. In this state of profound simplicity, the vast, cold, and empty expanse of one eon can be mathematically conformally rescaled or stretched to match the incredibly hot, dense, and tiny beginning of the next. The infinite future and the infinitesimal past become two perspectives on the same smooth, boundary-less transition. This is not a violent collision or a quantum bounce, but a graceful, mathematical metamorphosis where the end and the beginning are revealed to be the same point, seen through different lenses. But a new universe needs more than just energy. It needs structure, a reason to form galaxies. Penrose proposes a stunning source, the ultimate evaporation of all black holes through Hawking radiation. In the final phases of an eon, as the last supermassive black holes slowly radiate away their mass, they release all the information they ever consumed in the form of low-energy photons and gravitons. This process, Penrose suggests, could imprint gentle ripples onto the fabric of the conformally rescaled spacetime, creating the subtle seeds of inhomogeneity needed for the next universe to form stars and galaxies. In this visionary cycle, the most destructive objects in our cosmos become the creative engines for the next. It is a poetic and deeply elegant vision, where the universe forever renews itself, each eon inheriting a subtle imprint from the fading echoes of the last, connecting the death of stars to the birth of new worlds across an endless conformal bridge. But quantum mechanics offers an even more radical origin, where something emerges from a state of true nothingness. The ninth vision is the cosmic egg and quantum tunneling, a model that transforms creation from a deterministic event into a spontaneous possibility. Associated with physicist Alexander Vilenkin, this idea applies the bizarre rules of the quantum world to the entire cosmos. In the subatomic realm, particles can perform seemingly impossible feats, like appearing on the other side of an energy barrier without ever going over the top. This is quantum tunneling, a probabilistic leap from one state to another. Vilenkin's profound proposal is that our entire universe could be the result of such a leap. But what did it tunnel from? The answer is not empty space, as empty space is still a something with geometry and potential. The nothing in this model is a state of no classical space, no time, and no matter, a complete absence of the framework we call reality. It is the closest conceptualization to true nothingness physics allows. From this void, through a quantum fluctuation, a tiny bubble of spacetime could spontaneously nucleate, much like a bubble of vapor forming in a superheated liquid. This bubble would be a universe in embryo, a cosmic egg. Crucially, this nascent universe would not be empty. It would contain the precise conditions of a false vacuum, the high-energy state that drives cosmic inflation. So, upon its birth, this quantum bubble would immediately begin to inflate at a staggering rate, ballooning from a quantum speck into a macroscopic cosmos in an instant. In this picture, the Big Bang is not a singularity but a phase transition, a quantum jump from non-existence to existence. The implications are deeply philosophical. It suggests creation is not a unique, necessary event but a probabilistic one. Given enough time, or rather, outside of time, such a tunneling event could happen. Our universe, then, might be one possible outcome in a vast quantum landscape of potential realities, a single bubble that happened to nucleate in the infinite potential of nothing. It offers a scientific narrative for the ancient question of why there is something rather than nothing, answering that on the quantum level, nothing is inherently unstable, forever pregnant with the possibility of everything. The universe we observe is strangely hospitable to life, a fact that has long puzzled scientists. Why do the fundamental constants of nature seem so perfectly fine-tuned, allowing for the formation of atoms, stars, and planets? The 10th vision offers a provocative answer, not by changing the physics of the beginning, but by changing the very question we ask. This is the model of the anthropic landscape and vacuum selection. It begins with a profound insight from string theory, which suggests the number of possible stable configurations for the extra dimensions of space is not one or a handful, but an astronomically vast number, perhaps 10 to the power of 500. Each of these configurations corresponds to a different vacuum state, a universe with its own unique set of physical laws and constants. This is the cosmic landscape, a near-infinite array of possible universes. In a multiverse where every possible set of laws is realized somewhere, the question of why our universe has its specific properties shifts dramatically. It is no longer a question of a singular, special mechanism. Instead, it is a question of perspective and selection. In the overwhelming majority of these universes, the constants would be incompatible with the formation of complex structures, let alone life. They might collapse instantly or be composed of nothing but radiation, or have forces too weak to bind atoms. Universes like ours, with stable chemistry and long-lived stars, are incredibly rare islands in this vast ocean of possibility. Yet, we find ourselves on one of those islands. The anthropic principle simply states that we can only observe a universe capable of producing observers. Our pre-inflationary conditions, the specific quantum state that inflated into our cosmos, were not uniquely destined. They were simply one possibility among countless others, a random roll of the cosmic dice that happened to land on a configuration that permits galaxies, planets, and ultimately, beings who can look up and wonder about it all. This model is controversial because it feels like a retreat from explanation, replacing a mechanism with a statistical necessity, yet it provides a powerful, if humbling, framework. It suggests that the deepest features of our reality, the very laws of physics we seek to derive from first principles, may partly be environmental accidents, the local conditions of our particular cosmic neighborhood. Our search for a unique theory of everything may instead reveal a landscape of every possible thing, with our existence serving as the only guide to why this particular corner of reality feels like home. String theory's symmetries reveal a universe that could have been its own mirror image. This brings us to the 11th vision, the pre-Big Bang scenario. In this model, the cosmos we know did not begin from a hot, dense point. Instead, it emerged from a phase that was, in many ways, its exact opposite, a large, cold, and slowly contracting universe. The key to this extraordinary transformation is a profound symmetry inherent to string theory called scale factor duality. Imagine a universe described not by its physical size, but by a mathematical scale factor that represents how stretched or compressed space is. Scale factor duality reveals that for every possible description of an expanding universe, there exists a perfectly valid dual description of a contracting one, with certain physical properties inverted, like a reflection in a cosmic mirror. In the pre-Big Bang phase, the universe was in this dual state, vast and growing colder as it gently contracted. There was no singularity, no point of infinite density, because the universe was never infinitely small. Instead, as it contracted towards what would classically be a crunch, the stringy effects of scale factor duality took over. The mathematics smoothly transitions the description from a contracting, cold universe in one frame of reference to an expanding, hot universe in another. This moment of transition is the graceful exit, the event we perceive as the Big Bang. It is not an explosion from a point, but a cosmic rebranding where the universe flips its own script. The cold, diluted radiation of the contracting phase gets mapped onto the searing, dense plasma of the expanding phase. This elegant symmetry provides a complete, non-singular prehistory, a full narrative of what came before our fiery beginning. It suggests that the question of what ignited the Big Bang might be a trick of perspective. The moment we stopped looking at the universe in one way and started seeing it in another, like finally recognizing the face in an optical illusion. Gravity is the architect of the cosmos, sculpting galaxies and guiding the orbits of planets, yet it remains the most stubbornly enigmatic of all the fundamental forces. While the other forces are beautifully described by quantum mechanics, gravity, as described by Einstein's general relativity, resists this unification, leading to the infamous singularity where physics fails. But what if this is not a failure of nature, but a failure of our perspective? What if gravity itself changes its character at the most extreme energies, becoming predictable and well-behaved? This is the promise of the 12th vision, the model of asymptotic safety in quantum gravity. The core challenge is one of scale. In the quantum world, forces are understood through particles, the graviton for gravity. But calculations involving gravitons at high energies often produce nonsensical, infinite results, a problem known as non-renormalizability. It suggests that as you probe smaller and smaller distances closer to the Big Bang, gravity becomes wildly unpredictable. The asymptotic safety hypothesis offers a daring escape. Imagine a river flowing down a mountain. Typically, tracing the river upstream leads you to a single source, a spring or a glacier. But picture a different landscape, a high plateau where many streams converge into a stable lake before flowing outward. In this analogy, the flowing river is the strength of gravity as we change the energy scale, a process physicists track using renormalization group flow. The problematic infinite results point toward a universe where tracing gravity upstream leads to a chaotic, singular source. Asymptotic safety proposes that instead, the flow of gravity leads to a stable fixed point, that high-altitude lake. At this fixed point, which corresponds to the ultra-high energies of the Planck epoch, the properties of gravity become constant and predictable. The force does not blow up into infinity. It settles into a well-defined quantum state. This would mean that a theory of quantum gravity is not only possible but could be mathematically consistent all the way to the beginning. In this model, the pre-inflationary universe was not a lawless singularity, but a phase governed by this safe, high-energy fixed point of gravity. The transition to the hot Big Bang and inflation becomes a smooth evolution, a gentle flow from this stable quantum gravitational regime into the classical spacetime we recognize. The universe emerges not from a breakdown of physics, but from a perfectly coherent quantum state, a stable launch pad from which all of reality could unfold without ever encountering the confounding infinities that have haunted cosmology for a century. It is a vision of profound order, suggesting that even at the very edge of existence, the cosmos obeys a complete and consistent set of rules. Space itself may be the greatest illusion of all. The 13th vision, the emergent spacetime from entanglement, proposes a reality where the very stage of the universe is not a given, but a consequence of deeper, invisible connections. This cutting-edge idea from the frontiers of quantum gravity suggests that space and time are not fundamental ingredients. They are not the canvas upon which the universe is painted, but rather the painting itself, emerging from a vast, hidden network of quantum relationships. At the heart of this is the phenomenon of entanglement, that strange quantum link where two particles, no matter how far apart, share a single, unified existence. Measuring one instantly determines the state of the other, a connection that seems to transcend space. But what if it is not transcending space but actually building it? A profound clue comes from a formula that reads like a cosmic secret: ER equals EPR. This links two ideas that seemed utterly separate. EPR stands for the famous Einstein, Podolsky, and Rosen thought experiment about entanglement, which Einstein famously called spooky action at a distance. ER stands for Einstein and Rosen's later work on bridges in spacetime, what we now call wormholes. This equation boldly proposes they are two sides of the same coin. Every pair of entangled particles is connected by a microscopic, non-traversable wormhole, a tiny stitch in the fabric of geometry itself. In this view, entanglement is not a connection through space. It is the literal thread that weaves space together. Now expand this idea to the dawn of everything. The pre-inflationary universe could have been a seething, chaotic quantum state, a primordial soup where every constituent was maximally entangled with every other. There was no well-defined here or there, no distance, because the geometry of spacetime had not yet crystallized. The Big Bang, then, was not an explosion in a pre-existing void. It was a phase transition, a cooling and ordering of this quantum chaos. As this hot, dense quantum state began to evolve, those countless threads of entanglement started to organize, knitting themselves into the stable, smooth, continuous fabric of four-dimensional spacetime we experience. In this model, the universe began not as a place but as a set of relationships. Location is not a primary fact. It is a secondary property that arises from the web of quantum connections. The vast distances between galaxies and the flow of time itself are collective phenomena, emerging from the deep, invisible links between everything. It suggests a cosmos where the most fundamental truth is not where things are, but how they are connected, a universe born from a single, coherent quantum relationship that then unfolded into the spacious reality we call home. The fabric of reality may be woven from moments, not a continuous thread. The 14th vision, Causal Set Theory, proposes a universe built not from a smooth, flowing river of spacetime, but from a finite number of individual grains, like a cosmic hourglass counting out discrete instants of existence. In this model, the fundamental ingredient is the causal set, a vast collection of elementary events, each one a point in the history of the cosmos. What gives this collection its structure is not proximity in space, but a simple, profound relationship. One event can influence another. This is the causal order, the fundamental before and after that stitches the universe together from the bottom up. Think of your own life not as a continuous movie, but as a series of key moments: your birth, your first step, graduating, a first kiss, each one setting the stage for the next. The connections between these moments define your timeline more than the precise distances between them. In a causal set, the universe is born from a similar, but far more fundamental, network of cause and effect. The smooth, four-dimensional continuum of space and time we experience is not the starting point. It is an illusion, a large-scale average that emerges from this underlying, chunky, discrete reality. Much like a digital photograph appears smooth from a distance but is revealed to be pixels when you zoom in. In the earliest phases, this causal set would have been incredibly sparse, a bare scaffolding of fundamental events with vast causal gaps between them. There was no smooth geometry, no clear notion of distance or duration, only a growing web of causal links. The story of the pre-inflationary universe, then, is the story of how this sparse network rapidly complexified, how new events flooded in, filling the gaps and weaving a dense, rich tapestry of causality. As the number of events exploded, their collective relationships began to approximate a smooth, continuous manifold. The dynamics of this growth, the way the causal set unfurled, could naturally give rise to a period of rapid expansion, a phase we would observe as cosmic inflation. In this vision, the Big Bang is not an explosion in space, but the moment this causal network achieved a certain density and connectivity, allowing the familiar concepts of here, there, then, and now to crystallize from the pure relations of before and after. It offers a breathtakingly minimalist foundation where the universe begins not with a singularity of energy, but with a single, simple rule that events can influence other events, and from that seed alone, the entire majestic structure of spacetime and physics emerges. The final model asks us to consider a birthplace of profound darkness and transformation. The 15th vision is the thermodynamic and black hole genesis, a hypothesis where our entire cosmos is not a bubble or a bounce, but the interior of a black hole born in a larger parent universe. This provocative idea, championed by physicist Lee Smolin, weaves stellar death and cosmic birth into a single, breathtaking narrative of cosmological natural selection. Imagine a massive star in another universe reaching the end of its life. Its core collapses under its own gravity, crushing matter into an unfathomably dense state and forming a black hole. At the heart of that black hole lies a singularity, a point where the known laws of physics break down. But what if that breakdown is not an end but a transition? The mathematics of general relativity, when applied to a collapsing black hole, can be reinterpreted through a change of coordinates. The inward falling trajectory of matter, from the perspective of something crossing the event horizon, can be mathematically mapped onto an outward expanding trajectory in a new set of dimensions. That crushing singularity from another viewpoint becomes a hot, dense, rapidly expanding beginning, a Big Bang. In this model, our universe is that new interior, born from the gravitational collapse of a star in a cosmos that came before. This creates a staggering cosmic ecology where universes reproduce through the black holes they create. A universe that forms many stars and thus many black holes would spawn more offspring universes. Over countless generations, this process of cosmological natural selection could favor universes with physical laws that are efficient at producing black holes, just as biological evolution favors traits that lead to more offspring. This could explain the apparent fine-tuning of our universe, not through an anthropic landscape of random chance, but through a Darwinian process on a cosmic scale. The laws of physics in our cosmos might be the way they are because those laws are good at making stars that collapse into black holes, which then become new universes inheriting similar laws. It ties the death of a star, the ultimate act of gravitational destruction, directly to the creation of an entirely new reality, suggesting a profound thermodynamic and evolutionary link between the fate of one cosmos and the origin of another. So we have 15 radically different visions for the birth of everything. Each offers a compelling narrative, a mathematical framework that attempts to lift the cosmic curtain. But science does not advance on elegance alone, it demands evidence. The true power of these models lies not just in their stories, but in their predictions, in the subtle fingerprints they might have left on the cosmos for us to find. By comparing their strengths and challenges, we can see which are grounded in our current understanding of physics and which push us toward entirely new frontiers. The first critical test for any model is how it handles the beginning itself. Models like the no-boundary proposal, loop quantum cosmology, and the pre-Big Bang scenario achieve a major victory by offering non-singular origins. They replace the confounding point of infinite density with a smooth transition, a bounce, or a graceful exit, providing a complete mathematical description through the moment we call the Big Bang. This is a significant theoretical strength as it resolves the central breakdown in our equations. In contrast, models like eternal inflation or the anthropic landscape often incorporate a singularity as a starting condition within each bubble or cycle, pushing the ultimate question of a first beginning further back, but not eliminating it entirely. The next test is theoretical grounding. How deeply is each model rooted in established or promising frameworks of physics? String gas cosmology, the pre-Big Bang scenario, and the holographic principle are deeply entwined with string theory and quantum gravity research, drawing from active, cutting-edge fields. Loop quantum cosmology emerges directly from a specific approach to quantizing space-time. The asymptotic safety program works rigorously within quantum field theory. These models strive for consistency with our most fundamental physical theories. Others, like conformal cyclic cosmology or black hole genesis, are more speculative grand narratives, offering breathtaking syntheses of ideas but requiring new physics or interpretations that are not yet part of a mainstream framework. Their strength is their boldness and their power to inspire new lines of inquiry. Then comes the most crucial arena, observational evidence. What measurable clues did each model imprint on the universe? The primary cosmic fossil we study is the cosmic microwave background, the ancient light from when the universe first became transparent. Its subtle patterns of hot and cold spots are a treasure map of the primordial conditions. Most inflationary models predict a very specific statistical signature in these fluctuations, one that has been largely confirmed, but deviations from this standard pattern could be the key. For instance, certain models of loop quantum cosmology or a string gas phase might produce a distinguishable twist in the way temperatures correlate across large angles on the sky, a faint echo of the quantum geometry or stringy thermodynamics that preceded inflation. The hunt for primordial gravitational waves is another monumental test. These are ripples in space-time itself, generated by the violent energies of the earliest moments. Their detection would be a direct probe of the pre-inflationary energy scale. Some models, like certain versions of eternal inflation or a dramatic bounce scenario, could produce a stronger or weaker gravitational wave signal than standard inflation, offering a potential way to tell them apart. Future observatories like space-based gravitational wave detectors are designed to listen for this faint whisper from the dawn of time. Perhaps the most profound potential discovery would be evidence of a prior universe. Conformal cyclic cosmology makes a stunningly specific prediction that collisions of supermassive black holes from a previous eon would leave circular imprints or Hawking points in the cosmic microwave background. Some researchers claim to have found tentative evidence for these patterns, though the findings remain highly controversial. Their confirmation would be a revolution, offering not just a model of the beginning, but proof of a cycle. The challenge for many models, especially the multiverse theories like eternal inflation or the vast anthropic landscape, is testability. If our universe is one bubble in an infinite, eternally inflating sea, or one possibility in a landscape of 10 to the 500 universes, how can we ever observe the others? Their evidence may be indirect, relying on statistical arguments about the likelihood of our local conditions. This shifts them, for some scientists, from the realm of empirical science to that of metaphysical philosophy, a boundary the community continually debates. What this comparative analysis reveals is that the quest is gloriously unfinished. No single model yet commands the field with definitive proof. Instead, we have a spectrum of possibilities, each with its own virtues and its own open questions. Some seek to explain the fine-tuning of constants, others to eliminate the singularity, others to unify gravity with quantum mechanics. They are not all mutually exclusive either. Ideas from one often feed into another. The pre-inflationary universe might have been an emergent spacetime from entanglement that underwent a loop quantum bounce, for example. This is not a sign of failure, but of a field rich with imagination, rigorously probing the limits of reality. The ultimate answer may be a synthesis we have not yet conceived, a model that takes a crucial piece from several of these visions. Every new satellite mapping the cosmic microwave background, every gravitational wave observatory coming online, every advance in string theory or quantum computing brings us closer to reading those first lines of the cosmic story. We are detectives sifting through the ashes of creation, and each of these 15 models is a hypothesis, a different lens through which to examine the faintest traces of our genesis. This journey through 15 cosmic origins leaves us not with a single answer, but with a far more valuable treasure, a map of human curiosity itself. Each model is a testament to our relentless drive to look beyond the curtain of the knowable, to ask the question that seems to have no answer. In this grand endeavor, the rigid line between physics and philosophy dissolves into something beautiful, a shared space of wonder where mathematical rigor dances with profound speculation. We stand at a unique moment, armed with equations and telescopes, peering into the void not with superstition, but with a structured imagination, testing the very limits of logic against the silence of the cosmos. The fact that we can conceive of universes born from black holes or timeless geometries or quantum whispers from nothing expands our collective mind. It proves that the quest for origin is not a puzzle to be solved once and forgotten, but a perpetual engine of discovery, pushing our understanding of reality into stranger and more magnificent territories. While the ultimate truth of our pre-inflationary past remains hidden within the faintest echoes of the cosmic microwave background or the subtle tremors of spacetime, the pursuit itself reshapes our place in the universe. We are not just passive inhabitants of a finished cosmos, we are its conscious interpreters, gathering the scattered pages of a story written in the first instant and trying to piece together the opening sentence. This search for beginnings is, in its essence, a search for meaning, a fundamental human endeavor that connects the ancient stargazer to the modern physicist. If this exploration of primordial possibilities has sparked your own sense of wonder, consider joining the ongoing conversation. Your perspective is part of this grand investigation. Share in the comments which of these 15 visions resonates most deeply with you. Which idea of the beginning feels the most compelling or strange? And for more journeys to the edge of understanding, exploring the universe's greatest mysteries, subscribe and stay curious. The story of everything is still being written, and we are all reading it together, one breathtaking theory at a time.